Yes. We continue with the numerical methods and we discussed the bisection method this time. Bisecting the interval to narrow down the brackets or the range of the solution. So f of x is put 0, assumed to be 0, and then the product at 2 points f of a and then multiplied by f at b supposed to be less than 0. Okay, and then a mean is to be taken, which is an plus bn divided by 2 depending on the number of iteration or stage, let's say. So if we have a function which is x square minus x minus 1, okay, and the first thing we do is we do the arbitrations. Let's say f at 1 is equal to 1 square minus 1 minus 1 is equal to minus 1, which is less than 0, and f at 2, two numeric values are not decimal but numeric values which can be put in x. So 2 square minus 2 minus 1 is equal to 4 minus 2 minus 1 is equal to 1, which is greater than 0. You see, so f at a is less than 0 and f at b is greater than 0. So two situations, and now we check the product. F at 1 times the f at 2 is equal to what? Minus 1 into minus 1 is equal to minus 1 times 1 is equal to minus 1, which is less than 0. Okay, so this indicates that the roots exist in the interval AB. The assumed arbitration roots exist in interval A B. Okay, and the first mean is equal to what? Very simple, 1 plus 2 divided by 2 is equal to 3 by 2, which is 1.5. Yes, and now we estimate the function at 1.5. So it's a 3 by 2 whole square minus 3 by 2 for simplicity minus 1 is equal to what? 9 by 4 minus 3 by 2 minus, alright, we just simply put the fraction, the decimal fraction, the decimal values, 1.5 square minus 1.5 minus 1. So the situation is that we have 2.25 minus 1.5 minus 1 is equal to 1.75. Now this 1.75 is sorry 2.25 minus this is minus 0.25. This is less than 0. Okay, you see, if it is less than 0, we put m is equal to a. Therefore m is equal to a, and that means that now the interval is 1.5 and 2. 1.5 in terms of, in place of a, and b is 2. And now we take the second mean, and the second mean would be m2 would be 1.5 plus 2 by 2, which is 3.5 by 2, which means 1.75. okay, so 1.75, and now we estimate the function at 1.75, and this function is now 1.75 square minus 1.75 minus 1. Yes, so what we have is we will need a calculator for that. What we have this time is roughly 0.36, which is greater than 0, so m would be, in this case, b. Yes, so the upper bound would change, so the interval would be 1.5 and 1.75. Yes, see, 0.5 and 1.75. yes, so you see now the third mean can be estimated, which is m3, which would be 1.5 plus 1.75. Notice the shrinking of the interval, which gives us 3.25 by 2, which is 1.62. okay, so a point inside this interval, the mean, and then we estimate the value of the function at this point. The interval has contracted, and the situation becomes 1.62 square minus 1.62 minus 1. Yes, so the situation roughly now is the use of a calculator. Roughly approaching 0. okay, I cannot actually do the recording and do the calculator on the smartphone at the same time, but I've done the rough work and I know that this value is very small and very close to 0. So this shows that we have narrowed down and contracted the interval. Now the result is very fine. So as I mentioned earlier in the Newton's method, the thing is we have xy plane, understandably. Okay, you see, I'll tell you, x here, and we have this, let's say, f of x, function of x, and it intersects at a point here. This is the point of intersection, let's call it I, and this is the first solution that we have. Okay, and what we're doing is we are trying and narrowing down the interval on x-axis to approximate this point. So this is the solution, and this method approximates that interval and shrinks it down to a very small value, so that we can get closer and closer to the precise solution. Rough solution is easy. The precision of the solution matters, which is what numerical analysis or methods are about. It's worth the time showing the important properties of logarithms. Yes, so the general form log base a of m times n is what? Log base a of m plus log base a of n, yes, and log base a of m to the power n is n times log base a of m. This is 1, this is 2, let's say, and then we have this little log base a of m by n. Not difficult, just log base a of m minus log base a of n. So this is 3, and log base a of a is 1, and log, you see, log base a of 1 is 0. This is 4 and this is 5. We can do a little bit of practice on this. To use the first one, let's say log base 10 of 5 dot log base 10 of 10 to the power 2 dot 10 to the power 3. 10 to the power 1, let's say. So this will be equal to what? Log base 10 of 10 to the power 2 plus log base 10 of 10 to the power 1, which will be equal to 2 log 10 of 10 plus 1 log 10 of 10. So this will be equal to what? 2 dot 1 plus 1 dot 1 is equal to 2 plus 1 is equal to 3. The second form, for example, we have the log base 10 of 10 to the power 3. This would be very much 3 times log base 10 of 10 is equal to 3 times 1 is equal to 3. Log base 10 of 10 to the power, let's say this is fraction by n, so 10 to the power 3 by 10 to the power 2 is equal to log base 10 of 10 to the power 3 minus log base 10 of 10 to the power 2. It says what? 3 dot log 10 to the power 10 minus 2 dot log 10 to the power 10. This is equal to 3 dot 1 minus 2 dot 1 is equal to 3 minus 2 is equal to 1. Yes, and very simply log of 10 to the power log base 10 to the power log base a of a. So log base a of let's say 1000. So see, uh, log base a of a. Log base a of a means log base 10 of 10, which we have already shown is equal to 1, and log base 10 of 1 is equal to 0. Yes. So we have many more examples and also natural logarithms, but we will look into that later. For now, this is enough for the basics.